My name is Peter Flemings, and I'm very pleased to introduce today's UTIG seminar speaker, Alejandro Cardona Ramirez. Alejandro is a postdoctoral scientist at UTIG. He works in theory and experiments in fluid flow and porous and fractured media. And he's a postdoc working as part of the methane hydrates effort at UTIG. He has an office both at Pickle and downtown. And when we are all back in the office, we will be able to find him. He received his undergraduate degree from the Universidad Nacional de Colombia, and he received his master's and PhD from King Abdullah University in Saudi Arabia, referred to as KAUST. And his thesis was entitled Transport in Fractured Carbonate Rocks. Alejandro's doctoral advisor has a deep reputation in geotechnics in general, but also experimental developments, and was one of the leaders in early study of hydrates. He's been with us for about 8 months, but I can tell you in those 8 months, he's demonstrated remarkable skill and insight in the laboratory. And it's a pleasure to have him in Texas. And one thing I'll say is I put in the chat, the sign up, there's a few slots if anybody would like to meet with him this afternoon, or you can email me. And with that, Alejandro, we look forward to your presentation.
Well, good morning, everyone. Thanks, Peter, for the introduction. It is a pleasure to present this work to all of you today, flow phenomena in geomaterials, which sort of encapsulates what I did as part of my doctoral studies, but also includes a little bit of my work here as a part of my postdoc. And while these developments have focused or have emphasized in energy-related applications, the concepts that I will illustrate today, I hope that illuminate a variety of Earth processes that extend beyond energy. And we are talking about flow through faults, fluid-driven earthquakes, CO2 storage, just to name a few. And to extent of, oops, this is not, oh, let's see why this is not moving. Yeah. And to extend what Peter has just said, I joined UTIG roughly 8 months ago to study hydrate-bearing sediments as part of the Gulf of Mexico project. But prior to that, I did my PhD at KAUST, Saudi Arabia, a place in the coast of the Red Sea. And there our focus was on fractured carbonate rocks. It's an important resource for the Middle East, but also for the world. But truly my energy drive, or my research in energy, it all started in my undergrad back in Colombia, where I did my bachelor in petroleum engineering. And there I started to realize the importance of coupled processes. That is not only flow that we typically think in the petroleum context, but also mechanical processes particularly. Now, out of this presentation, I hope to convey the following messages that you will see throughout. First, we will see how energy is really important to us at the individual level because it's intimately related to quality of life. And within that context, I will talk about 3 different geomaterials: carbonates, fractures, and hydrates. In carbonates, we will see how the underlying predictor for permeability is the pore size. In fractures, we will see how they vary in a wide range of spatial scales. And that poses a problem, a challenge. How do we study something that varies that much in length scales? And that's where we use fracture digital analogs. And with hydrates, we will see how they affect all properties, but there is a challenge as well. We need to maintain the hydrate within stable conditions in order to analyze those samples and to study those processes. And that from the experimental point of view is a challenge, and we'll see a little bit of that. Now, let me start with the first question, and why energy is so important. And I want to, or I hope to clarify that question with this data, right? Each of these data points represent a different country in the world, and here we have the United States as a reference. In the x-axis, we have the energy consumption per capita, or more precisely, the power consumption per capita. And each of these different plots show a different qualifier that somehow relates to quality of life. And it's remarkable to see this trend. As energy consumption increases, water access increase, life expectancy increase, mean years of schooling increase, and infant mortality rate decreases. Now, this is quite remarkable because these qualifiers, you may think that they are not related to energy at all, but the correlation is clear. Now, we can look deeper, or we can dig deeper into this data, and we see that somewhere around here, 1 kilowatt per person to 5, there is some sort of threshold. And then the first two plots here show more clearly that. And what this threshold means is that after this point, this curve tends to plateau. And what it precisely means is that in terms of quality of life, we don't gain much, and we don't gain anything if we consume more energy. Doesn't matter if you are here or if you are here. In terms of quality of life, it more or less is the same. So the energy strategy here is that to reduce the energy consumption in these energy-intensive countries, and for us for the geoscience and geoengineers to provide the means for these countries, for their individuals to increase their quality of life with energy, right? Now, where does this energy come from? And where does this energy will come from? And here I have plotted the US as a reference, and worldwide trends may be a little bit different, but let's use the US as an example. Here we have energy consumption segregated by the different sources with time, right? And before this dashed line, it's all historic data. After that, this line is all projections, right? And clearly hydrocarbons, petroleum, gas, and coal have been the dominant in the energy mix. Today, they represent roughly 80% of the entire energy mix. But for the future, clearly, renewables will play a critical role there. But what is also important to recognize is that the importance of fossil fuels or hydrocarbons. And while these percentages may decrease or remain roughly the same, the actual consumption of hydrocarbons will increase. And that's a manifestation that we as humans, we are growing in human population, we are increasing the numbers, so we need more energy. And we, at the individual level, we require more energy to increase our quality of life. Now, what is the role of the geoscience in this context? And what we have adopted here is what we call a geo-centered solution. And these tables hope to exemplify that. Here at the top, we have the resource, and here at the bottom, we have the implications, more or less. And clearly, the geoscience have been the leading the fossil fuels development, and more recently in the renewable side, in the geothermal. And within this context, or within these applications, the geoscience prevails in the characterization, in the infrastructure, and the extraction per se. Now, what's the role of the geoscience in the renewable, particularly in solar and wind? And here is where the energy storage comes into the picture. The intermittent nature of these systems implies that we need to store the energy to consume it when this energy is not available. And there are different strategies in the geoscience community that allow us to do that. Now, in these other systems, in petroleum, gas, coal, and geothermal, we have to store all of that waste, what we call the carbon-based storage. And here we're talking about CO2, produced water, produced soils. And finally, within the nuclear context, we have all that waste as well, the nuclear waste that we need to deposit safely. So clearly, the geoscience prevail in all these analyses, right? The geodisciplines will play and will play a crucial role in the energy challenge. Now, particularly, what is the role of flow within this context? And here I'm just trying to show this simple example. Imagine you have a resource here and you want to extract that resource. One possibility is that you will inject a fluid, let's say water, and that water will displace that resource there. And that resource can be hydrocarbons, what we have typically thought about it, or it can also be heat in the context of geothermal, right? And what is important to recognize is that this is flowing, this is displacing fluid, this is displacing the resource. And associated to that flow, there are a variety of processes that are coupled, what we call hydrochemothermomechanical coupled processes. And just to show you an example, imagine that instead of injecting water, we inject CO2 in a carbonate reservoir. If we inject CO2, we will create carbonic acid that may start to dissolve that carbon. So clearly chemistry there plays a role. And when we talk about geothermal and heat extraction, clearly thermal processes will be involved there. So flow is critical for all of these energy processes and of course the associated environmental implications. Now, in this presentation, I will talk about 3 different geomaterials. I will talk about carbonates, particularly about permeability, and how these pore scale extraction affect permeability estimation. We'll talk about fractures and how flow and stresses, mechanical stresses, are coupled. And finally, I will talk about hydrates and how the fact that we have hydrate, water, and gas affect flow. Now let's start with carbonates, right? And carbonates are very interesting materials because there's a saying that says carbonates are born, not made. They have this biological origin. And as a consequence of that origin, you have features such as this one, where you have porosity associated with this entire grain, right? But you have porosity inside the grain, what we call intragranular porosity. And now the question here is, what is the implications of this phenomenon or this effect in terms of permeability estimation purposes? Now, why carbonates? Why carbonates? Why we want to understand carbonates? And the reason for that is this is the distribution of petroleum reservoirs or hydrocarbon reservoirs around the world. And clearly for the Middle East, they are the dominant there. And in fact, in the world, they represent 50% of the hydrocarbon reserves. And since we are talking about energy extraction, we're talking about flow, permeability will tell you how fast those resources will be recovered. Permeability is critical in all of these analyses. And when we go and try to look on the permeability estimation models, we see that these models have a high degree of uncertainty. And that's not acceptable, right? This degree of uncertainty in terms of orders of magnitude cannot happen if we think of energy extraction purposes. So we decided to, okay, let's go back to the fundamental. What really controls permeability? Let's go back to the physics. And one way to do that is to using these simple models, from single tubes to porous medium. And the use of these models, these cylindrical models or these cylindrical tubes, is that they allow us to come up with analytical solutions very simple. And when we compare the analytical solution of flow in a tube with the macroscopic representation of Darcy's flow that describes how fluids flow through a medium, we see certain commonalities there. We have the pressure gradient here. We have the viscosity here that is common in the 2 equations. And here K represents permeability. And here when you compare this K with this equation, you see that permeability tends to be related to pore size. And in fact, to the square of the pore size. Now, pore size is a tricky parameter to measure, right? So instead of measuring per se, what we can do is estimate it with properties, or with what we call index properties, that can be more easily measured in the lab. And that's porosity here in phi and a specific surface. And a specific surface is the surface area that a porous media has over its weight. And here rho is density, which is easily measured. But before jumping into analysis, let's see how the data looks in terms of porosity and a specific surface. And that's the plot that we have here on the right. We have compiled data from the literature, and clearly, as a specific surface increases, permeability decreases. And when we take a look at this in terms of porosity clusters, there is some sort of correlation there. So that's interesting, right? Now, let's use this simple equation to estimate pore size and see how it behaves with permeability. And when we do that, we see how all this data cloud emerges or collapses onto this narrow trend. That's quite surprising, and that's quite remarkable. Now, what is the slope of this main trend? That slope is 2, which in this log-log space reflects a square dependency, which is originally anticipated by that simple flow-through tubes model. Now, you may ask, what happened with these outliers? And in fact, it's the half of the specimens that we tested. Why they are not in the main trend? That may suggest that this pore size estimated from these qualifiers may not work for all these cases. So which one is the actual pore size that works? And we did that, or we explored that question by using a technique called mercury injection or mercury pore size distribution. And the idea here is that we inject mercury and we get curves such as this one. We have a cumulative distribution of pores versus the pore size itself. So what we explored was different pore sizes or different percentiles of that cumulative distribution. So for example, when this is 95%, that will represent the D95 pore. And when this is 80%, this will be the D80 pore, the 80 pore, and so forth. So what we see here on the left, this data cloud, is that the correlation is not so good with large pores, this D95, and it's not so good with small pores, this D30. There is so much dispersion. It seems to be good when we have the D80 percentile, right? And why is that? It's because this is the largest pore size, and pore size, again, large pore size means lower drag, viscous drag, but it's the largest pore size that forms a percolating path, what we call a continuous flow path. So clearly D80 is the one that it seems to correlate with this permeability. Now, this is good. So, and this model may be so trivial. So what about if we use more complex model and we did what we call a blind test? We start to test other models in the literature that also use mercury pore size distribution data. And here we have our model, the D80 percentile, and this plot shows estimated permeability versus measured permeability. And when we compare our simple model with more complex models, we see that the level of uncertainty is equally in all of these models. We have the same accuracy or the same predictability with any of these models. But the advantage of this D80 model is that it's much simpler to implement. Now, let me summarize this section by saying pore size is the best estimator for permeability. It's the one that truly captures the physics of what permeability is about. And this estimate using the specific surface and porosity, it works, it's easy to implement, but in some cases it may not work because at the end of the day, it does not capture that continuous pore size, this D80, right? And that's critical in carbonates because carbonates have this dual or this large pore size distribution due to its intragranular porosity. Now, with these models, we realize that there is an irreducible uncertainty. There is roughly 1 order of magnitude from these correlation-based estimates. But we should stick to the ones that are simpler to implement, and we believe this is the D80 model, what we call it. But with this uncertainty, we should ask ourselves, okay, should we keep doing these estimates from pore size based on the fact that they have this uncertainty? Well, clearly when we don't have another option, right? When specimens are limited to small sizes. But when we have specimens, we should measure this property to have true value rather than a correlation estimate. Now let's go with fractures. And fractures are also very interesting in geomaterials because fractures represent what we call points for localization. And to illustrate that, I have this image, what is called a photoelastic image. And here we have and the photoelastic effect or the photoelastic process is that there is a material that changes its optical properties when it's subjected to mechanical stresses. So here we have a fracture, and clearly these fringes show that there is concentration of stresses and deformations near the fracture tip or near or around the fracture. So clearly fractures localize deformations. And it turns out that they also localize flow. Now, why fractures are important and why should we care about them? And here I just showing you the example of geothermal, in fact, deep geothermal. And the idea of geothermal is that you have a resource that is really hot and you want to extract that heat, right? And the way we do that is that we inject cold water into this medium. The water will be heated up and then we will recover hot water. And that we will use, we will extract that heat to produce electricity, for example. Now, there is a caveat here, there is a problem. These rocks, typically, they have very low permeability. So how do we flow when the system has a very low permeability? So what we do is to artificially create fractures, or we use natural fractures that are there to allow flow, right? So fractures, it's prevalent in all this analysis, and in fact, it's critical for this technology to succeed. And when we compare the amount of energy that is stored in these systems, in the geothermal systems, we see that it may be quite significant, and in fact, maybe double or triple the amount of fossil fuels. Now, with fractures, there is a problem, right? When we compare how fractures vary in nature, or mechanical discontinuities vary in nature, we see that they vary in a wide range of spatial scales. Here, this is a logarithmic scale, and look the amount of variability that mechanical discontinuities exhibit, from lattice dislocation at the molecular scale all the way to plate boundaries. And let's say that we narrow our interest there, and we narrow what we call fractures here in this range. And this is still a quite large range. We're talking about 6 orders of magnitude here, 5 orders of magnitude. And it's a property that we don't see in other types of structures, in pores, in cells, or on geological structures, right? So how do we study these things? And in fact, what is the common parameter for these fractures and these fractures, right? And that parameter is what we call surface roughness. And here, to illustrate that, what we have done is to compute what we call the roughness power spectral density, this parameter G, which tells you information about the amplitude of an asperity. G is related to the amplitude of that asperity. And here in the x-axis, we have wavelength, which tells you how wide that asperity is. And what we have done here is to compile data from the literature. So these are these points. We have measured surfaces in the lab, and we have computed this pore spectral density, and these are the solid lines. We have also used standard roughness profile. We have digitized them and put them in this framework. And this is remarkable to see this trend. And what this trend tells you is that the relationship between amplitude and wavelength for large fractures, here let's say we are talking about 100-meter fractures, that relationship between these two quantities is more or less the same than for a really small fracture of, let's say, 1 millimeter. And this makes sense, right? The larger the fracture, the larger the asperity that you may expect. But what is interesting is to see that there is a commonality there in that relationship. And this is very neat because it allows us to create numerical surfaces and start to play with different concepts, right? And that's what we did. We create numerically or artificially, we create what we call these digital analogs for different fracture sizes, right? 0.1 meter, 1 meter, 0.01 meter. And you see how remarkable or how striking is this when you compare it with experimentally measured surfaces. And of course, the larger the fracture, here the color bar shows the variability of the roughness. The higher the fracture, the higher the variability, right? So this is nice. We have this technique that we can use to study processes. And that's what we did. We first study with the concept of matedness. And matedness reflects how two surfaces are correlated. So to analyze this in terms of end members or extremes, we have a perfectly mated fracture here, where the two surfaces are a mirror of each other. And in the other extreme, we have an unmated, perfectly unmated fracture. There is no correlation between this top surface and this bottom surface. And what we study here is how the aperture, the space that are between these two surfaces, how that aperture distribution, because it's a distribution, it varies, how that distribution evolves as we start to shear these fractures, or we start to displace these fractures in shear. So for a perfectly mated fracture at zero shear displacement, clearly there is no aperture, so this is 0. But as we start to shear, the system starts to dilate, starts to expand. These surfaces start to ride on top of each other. And that's what we see here as we increase this shear displacement. This mean value increases and the variability of those aperture increases. Now, with unmated fractures, this is something very interesting. It doesn't matter how much you shear it, if you shear it a little bit or if you shear it a lot, because the shear makes sense when there is correlation between the two surfaces. But for these perfectly uncorrelated surfaces, it doesn't matter if you shear it too much or a little. Statistically speaking, the aperture size distribution will be the same. And just for you to know, each of these lines is the results of multiple numerical realization. So these are statistical values. Now, what we did next is to study flow, flow in the context of mechanical coupled processes. And here we have the effects of normal stress and shear displacement. So with normal stress, as you see, is that as you start to increase the normal load, these channels start to dominate the flow, what we call flow channeling. And flow focuses on these particular channels here. With shearing, we have another interesting effect. As shear progresses, contacts transverse to the shear direction detach, and you create these topographic ridges. And the consequence of that is that you will have flow anisotropy. Flow will preferentially go in this direction than in this direction. Now, to extending these studies, what we did was to study this from the lab perspective. And once again, we are limited by the size, but just to have a more controlled environment here. And we developed this setup, this experimental setup, where we have a pre-fracture specimen that it sits here, right? And using this, what we call this hydraulic jack, we can apply normal stresses to the fracture plane, and we can apply torsional stress or displacement or torsion in these specimens. And at the same time, we have a fluid injection port through this bottom specimen here, this bottom plug here. So at the same time, we can apply normal stresses, shear and flow, and we can study how these things change as we change these parameters, right? And we can measure these things while we do all that. Now, typical data shows that as the effective normal stress increases, the transmissivity, which is the equivalent of permeability for fractures, decreases, right? It makes sense. As you compress the fracture, the transmissivity decreases. And now with shear, we can see that as shear progresses, and depending on the level of matedness, you can dilate, you can expand this, and the transmissivity will increase. Or at the beginning, it can contract, and this is a typical signature that we see in shear systems. At the beginning, contracts, accommodates, and then it increases or it dilates, right? But this is neat, this is nice, but we need to be able to anticipate these processes or to implement this processing in numerical simulators, right? And these are the models that we have developed here, these solid lines. And what is interesting is that, yes, we are anticipating the behavior in the range or in the range of stresses and displacement that we're interested in. But in terms of numerical implementation, we also take a look at the extremes. What happened at the extremes? When we implement these equations, these mathematical expressions in simulators, we should look at the extremes because they may, if they are not considered, we may get unrealistic values, or we get numerical instabilities. So what we have proposed here is two models and mathematical expressions that are asymptotically correct. At the extremes, they tend to plateau, right? These things won't go to infinite or to zero or things like that. Or at least we want to control the value at the extremes. And that's what we do here at infinite stresses and zero stresses, and the same for shear. Now, to make these mathematical models more robust, what we did was to compile data from the literature. And here we have superimposed our experimental data and or compiled data. Each of these different markers represent a different test, here in terms of normal stress, and here's in terms of shear displacement. And clearly our models or captures quite well the behavior in each of these cases, either in normal stress, right, or in shear with this S-shaped trend that we see in shear. Now let's analyze something, and since we are talking about energy-related applications, multi-phase flow is everywhere, right? And here I want to illustrate that, or to recognize the implications of that with this example. Here is, okay, let's say we inject CO2, and this plume will go into this area, right? But what we want to ask is, okay, inside this area, invaded area, what is the fluid distribution of that fluid, right? And to understand or to hope to answer that question, we need to take a look at the fundamental physics of this problem, right? And here what is prevailing are capillary forces and viscous forces. With the help of these, what we call phase diagrams, we can anticipate what will be the invasion morphology, the invasion regime, right? So if, for example, the viscosity of the invading fluid is much larger than the viscosity of the defending fluid and capillary forces are neglected, we can see how this displacement is very stable displacement. Now, if capillary prevails or viscosity of the invading fluid is very low, what we can have is these fingering effects, right? And the implications of this that we will have much lower displaced fluids that we would expect when we do these kind of things, right? And here I'm just putting the example of CO2, but this has a relevance in a variety of problems, right? Anything that has to do with multi-phase flow, hydrocarbon extraction, vapor liquid transport in geothermal, and so forth. But this is in the context of, let's say, homogeneous porous media, right? Here we want to ask, okay, what is the implications on fractures? And since we're talking about more micro-scale phenomena, it seems intuitive to study this from the microscopic point of view. And we use a technique called microfluidics, right? And in the microfluidics, we design these micro models, and to represent the fracture media, we have these large pores here, and within those, or fractures, I would say, and within those fractures, we have what we call the intact rock, the matrix component, right? And we want to understand those processes. And I have a video of that, and hopefully this video will work. In the left, we have the injection at very low flow rate, and this is the speed of this has been accelerated. So this is not real speed time. And I hope you're seeing the video, right? Clearly, the invasion is first through the matrix, through the intact rock component. And the reason for that is that at these very low flow rates, the matrix capillary suction prevails. The suction is putting this fluid here in the matrix first, because lower the pore size, the higher the suction, right? So fluid invasion will occur first in the matrix. And let me reproduce that one more time. Now, at high flow rates, we have a different physics, right? At high flow rate, viscous forces will dominate. And if viscous forces dominate, with the displaced fluid will go preferentially through the fractures first. And as a consequence of that, if we have intersecting fractures, we will have these pockets of non-displaced fluid. This will be trapped, right? And so the question is, how do we recover this when this has occurred, right? Now, let me summarize this section of the fracture component by saying, look, there is an inherent limitation when we study fractures because they vary in a wide range of specialty scales. And that with that thought in mind, what we can do is to create fracture digital analogs to allow us to upscaling, right? And with those digital analogs, we have studied a variety of processes. We have studied matedness and how shearing prevails when we have some degree of correlation between the surfaces. We studied flow channeling that develops as a consequence of increases normal stress. We saw that shear displacement promotes flow anisotropy. And these concepts and experiments, we were able to create models, transmissivity models that anticipate the behavior in the scale, in the range of interest, but also represent the behavior at the asymptotes, at the extremes. And finally, in multi-phase flow, we saw how fractures add emergent capillary effects, and that's a consequence that we have a high contrast between sizes, and different forces will dominate depending where you are. Now, this is the last part of this presentation. We'll talk about hydrate-bearing sediments, and some people call this fiery ice. What hydrates truly are these solid structures that within these water cavities there is gas present, right? And particularly there can be methane, and that's our interest, the methane that is trapped in these systems, right? And you see that the methane hydrate, it's in the pore, so it's represent a phase within the pore space, right? And we want to understand, okay, what kind of processes and flow processes are there? Now, why hydrates are very important, and here I'm showing you the distribution of hydrate-bearing sediments around the world. Each of these data, these little points here represent the location where hydrate has been identified, and they tend to be near continental margins, right? And they tend to be near in really cold regions, right? Here in what we call the permafrost, and there is a reason for that. Now, what is interesting is that for countries that are typically energy importers, such as Japan, South Korea, just to name a few, this hydrate can be a potential resource to have a local supply of energy. Now, hydrates occur typically in submarine environments or in offshore environments and in permafrost environments. And the reason for that is that hydrate needs to be stable, and that stability conditions are within a certain range of temperature and pressure that occurs in submarine environments and in permafrost environments. So here we have what we call the hydrate stability zone in a submarine setting. The temperature decreases as we go down to the bottom of the seafloor, right? And as we hit the seafloor, the geothermal gradient kicks in and it starts to heat up the subsurface, right? So the hydrate, once again, is stable at low temperature and high pressure, and that constrains where the hydrate will occur, which is in this region specifically. Now, why hydrates are so important and what are the associated implications of hydrates? And here we can think of two time scales, let's say. In an energy resource or in production time scale, we need to assess, okay, this hydrate will be dissociated once we start to produce that gas. The hydrate will not be in the pore space. And then we need to ask, okay, what are the implications of that effect, of that phenomenon? And what could happen is that we can trigger instability of the slopes, or in this type of systems, we can trigger subsidence, just to name a few examples. Now, in geological time scales, we can think of, okay, what happens if the sea level changes or if the temperature changes, right? The temperature will be affected, or the pressure will be affected. And as a consequence of that, the hydrate may dissociate. And once again, it may lead to geohazards such as slope instability, or may lead to the release of gas plumes, right? And we need to assess this in the context of the carbon cycle. Now, the hydrate dissociation is an extremely rich process, a physics-rich process. And imagine you have these grains, right? And you have the hydrate here, and these little black dots are fines, grains that are much smaller size than this. And once you dissociate the hydrate, many things occur at the same time. First, you have high gas, so the fluid there will be a tremendous volumetric expansion. The fluid will tend to expand, and we need to think of what are the implications for the stability of the system, for the stresses that are acting in the system, the pore pressure, and so forth, and so on. These processes are very energy intensive, so hydrate, in order to dissociate, is to remove heat from the surroundings, so there is heat transfer across this. And we need to think about thermal processes or thermal conduction in this context, right? If the pressure increases too much, what we can form is fractures, so we need to think of fractures as well, right? Now the hydrate is gone, so this stability that the hydrate was having or imposes to the system is gone, and it may lead to sediment contraction. And now these little fines that were there, what we can do is, or what could happen is that this gas will displace those fines, they will accumulate at these throats, and it may affect the flow behavior of this system. So hydrates, once again, is an extremely rich process. And when we analyze specimens in the X-ray, and we see that after dissociation, we see all of these marks of where the hydrate was dissociated and leave these empty spaces. And we need to ask, okay, where the flow will go, what are the implications of that in terms of mechanical properties and so forth. Now, to understand hydrate, we need to maintain the hydrate within the stability conditions. We cannot study sediments that were the hydrate dissociated. It won't represent what is happening in situ. So as part of the UT led an expedition to collect samples from the Gulf of Mexico, to collect them at pressure. And this is a photo of one of those pressure coring devices that maintains the hydrate within the stability condition. And from these little chambers, we transferred the hydrate to these storage chambers, right? And when I came here to the group, we said, okay, this is the chamber that we have. We have done some measurement. How can we analyze these samples further? And the developments that I have done here in this group has been in this setup precisely, right? And this setup allows us to understand processes and behavior and to characterize these sediments by applying stresses to the sample, but also allowing flow through this sample, right? Just for you to have a sense of how the scale of this setup, this entire system that I'm showing you here is this little system here. So one critical question here is, okay, how do we put the specimen from that storage chamber to here, right? And there is a lot of incremental developments to allow to do that, to allow to increase the stresses that we impose in the sample and to make sure that what we measure is correct. Now, before I joined the group, we were conducting measurements, and these are different measurements of different samples, right, of pressure core samples. And we were able to measure porosity, permeability, and the lateral stress, which, while it not represents flow per se, it's an important parameter because it allows us to inform us to, okay, what are the in situ stresses when these systems do not deform laterally? And that's an important quantity to have in mind, right? But while we were measuring this and we were analyzing processes with this data, we didn't know if these measurements were correct or not. And there is a saying in experimental, or for us experimentalists, that says what we measure, what we think we measure, and what we really measure. So how do we validate this measurement? How are we sure that these measurements are correct? And what we did was to artificially create samples using a technique called resedimentation, where from this cake mix, if you say so, we'll create samples such as this one here that we can carefully control its properties, and we can also rely on typical devices to study samples like these, and we have comparison points. We can conduct benchmark studies to say, okay, with this traditional device that has been in the geotechnical community for years, that we are confident that what we measure is correct, we can compare those properties with our pressure coring tool or pressure coring analysis tool. And that's what we did here. We have porosity, permeability, and this lateral stress ratio. The solid line represents the typical device used in the geotechnical community, either consolidometers or triaxial devices. And these markers are our measurements using our pressure coring tool. So it's just remarkable to see that using two extremely different technologies, we are measuring the same thing. And it gives us the confidence that we need to understudy processes in hydrate-bearing sediments. Now, what type of processes we are interested in? The production of gas, of course, and I mentioned the processes associated to that. The dissolution of hydrate with inhibitors, right? What happens if we inject inhibitors on how we gradually dissolve this hydrate? And of course, we need to think this in terms of time scales and what are the implications of time in these systems. Now, to summarize this section, I think we have seen how hydrates affect all sediment properties, and particularly we're interested to study dissolution, creep, and gas production as part of my postdoctoral work. And to do so, we rely on a technology called pressure core technology that preserves the hydrate within the pores, right? And it allows us to study things with the hydrate in stable conditions. But that is extremely challenging, it's extremely difficult because all of those measurements need to be done at high pressure and low temperature. And here at UTIG, over the last months, we have done some magnificent technology developments that allow us to increase the capability of our system, but it also allows us to validate these measurement systems. Now, let me summarize some closing thoughts. So we have seen three different geomaterials. And we first start by analyzing energy, why energy is so intimately related to us and why it's important to us, particularly for quality of life purposes. In carbonates, we saw how pore size is the estimator for permeability, truly is the one that captures permeability. But all of these correlation estimates have an irreducible uncertainty, and that we should minimize whenever possible. With fractures, we saw how they vary in a wide range of spatial scales, and that's where we use the digital analogs to study different phenomena there. We propose models that are asymptotically correct, that reproduce the value or anticipate behavior at the extremes, and that's an advantage for numerical implementation. We also saw capillary, emergent capillary effects due to the contrast between the fractures and the matrix or the intact rock. And with hydrates, we saw how the hydrate affect all properties, and how to understand processes in the hydrates, we need to rely on pressure core technology, which is an extremely difficult tool. With that, that's all. Thank you for listening.
Alejandro, thank you very much. It's 11:20. You may not see it, but there's some yellow hands clapping. And I'm sure Alejandro would be happy to answer a few questions if there are any.
Hi, everybody. I have a question if you would, Alejandro. I really appreciate it. I like the talk. It was really fascinating. I love laboratory experiments. And I was wondering if you all had ever looked at like pore throat size distributions in looking for permeability. And also, I don't know enough about petroleum reservoir engineering. As my understand it, you're pushing mercury through your samples. What's the effect of like imbibition and drainage of, when you go to multi-phase on what you would see in the lab versus what you all did?
So very good comments, very good questions. So mercury injection porosymmetry, that technique is a proxy, or it's an approximation of the pore size distribution. And in fact, that you correctly mentioned, it's an approximation of the pore throat distribution. Mercury, what it actually measures is the throat of those pores, right? And with mercury, we use mercury because mercury is an extremely non-wetting phase. In a variety of materials, we know that mercury is a non-wetting phase. And what does it mean? It means that we can carefully control the injection. If we increase the pressure of the mercury, it will invade the pores, right? It won't invade naturally, or what we call in the imbibition. It won't invade naturally by capillary forces. We externally have to impose a pressure to invade that. And that's why we use mercury. Now, mercury allows us to get the pore size distribution, right? And with that pore size distribution, we can study processes that are related to imbibition or drainage, which is the mercury injection, right? Yeah, like typically materials so the imbibition and drainage component is related to the wettability of the system. So typically materials are water wet. So if we inject water, the water will go into an imbibition regime. If we inject oil or if we inject gas, it will go in a drainage regime. So it truly depends on the application and the purpose of the injection.
Thank you.
Alejandro, I had a question. In the case of the shear and the preferential flow, I think I know the answer, but the question is, the flow enhanced in the direction of the shear or orthogonal to the shear? That's my first question. My second question, in that D80 example, do you think materials that aren't carbonates would have a different characteristic pore size?
So related to the shear, yeah, the flow will be enhanced perpendicular to the shear direction. And the reason for that is because as you shear a system, you increasing the number of contacts in the shear direction. And therefore you are decreasing the contacts in the direction perpendicular to shear. And since you're decreasing the contacts, you're widening the pore, the aperture is there, and then that's why flow preferentially goes. Now, related to the D80, I think with this D80 applies for many geomaterials because it represents the largest pore size that forms a continuous path. And while we have not tested this for materials that are not carbonates, I believe that it will be a similar value, somewhere between D80, D85 to the D70 or so. But I cannot give you an answer. I don't have the data to support that statement.
Okay. And we have two questions. We'll start with Damien and then move to Madi here.
Yeah, great talk, Alejandro. My question actually follows on Peter's question about the shearing. And I guess just to make sure I understand correctly. So in this model, that change in permeability with shearing is caused by essentially dilation or sort of topography of rigid fracture walls as they ride over each other. In other words, if this were a softer material that had grains, for example, that could reorient, one might expect a different result, I think. Does that make sense?
It does make sense, yeah. Our models are, as you said, a rigid solid motion, right? We don't deform the asperities at all. We don't break those asperities. And yeah, absolutely, as you shear, you may start to generate fines or broken material. that may affect the flow and may affect those analyses. Absolutely, yeah.
Thank you.
Marty, go ahead.
Hello.
Yes.
Alejandro, great presentation. I enjoyed it. So you mentioned that you validated your permeability measurements by grinding some sample and packing that in a apparatus, right? So can you explain a little bit more about that? So how did you relate that permeability measurement for a sand pack or a ground material pack to the field samples?
Oh, I love that question.
So the idea of the resedimentation protocol, the resedimentation technique, is to create highly homogeneous samples that we can, if we do it once, we will do it next time, we'll do it tomorrow, and it will be the same. That's the idea, to have consistent creation of samples. Now we use very fine material, right? Because the fine material allows us to do this, the protocol that we did. If we increase them, if we think of coarse sand packs, this protocol will change. Now, what we do specifically with this fine grain material is that, okay, you saw that cake mix. We prepare that cake mix. We homogeneously distribute that fine material with water, right? We carefully remove the air that may be trapped inside, right? And then that cake mix, the air cake mix, we put them in a tube and we gradually increase the stress or the force that is applied to that tube. We do that. It takes roughly, it took us for this test 3 weeks to create that particular sample, because we allow the fluids to dissipate completely before applying the next load step. Now, how does it relate to the field specimens? Well, that's another question. Here, our idea was to, okay, let's have homogeneous samples that we can test in different tools, the classical geotechnical tools and in our pressure cooling tool.
Yeah, thank you. So I just wanted a little bit more about how you consider heterogeneity of the material in the field sample with respect to the one that you considered.
I think that's a good point. I think that's an inherent limitation of this resedimentation protocol. By definition, we are creating homogeneous sample, right? So heterogeneity will not be captured, at least with the protocol that I have in mind. I don't know if Peter, that has more experience with this procedure, can extend on that.
I was going to make one comment just for the broader audience. One of the key parts of that technique is that we use real parent material. And by that, I mean, we don't take some synthetics off the shop. We take cores that we've had previously. We try to pick one lithofacies and we try to homogenize that and then reanalyze it. And there's no doubt that there's extraordinary heterogeneity, for example, in any ocean drilling borehole. But one of the challenges in our research is that there's so much heterogeneity, you can't start measuring one thing consistently to understand behavior. So while there's a drawback that your prepared samples are all identical, it allows you to systematically explore things. So there's ups and downs to it. And Alejandro or I or anybody in our group would be happy to talk about it, because I think it's an important augmentation of sampling just intact rock.
Yeah, great. Thank you so much.
Let's see, Alejandro, it is 11:28. And I don't think I see any more questions. I want to thank you for an excellent talk. I want to thank the audience for all taking the time to join today. And I hope, take a good look at his picture there. And when you run into him in the hallway on Pickle campus, say hello. So thank you, everybody.
Thanks.